Okay, Quadratic Equation advanced. Fine. Question number one. A tenfold increase in pressure on the reaction at equilibrium results in something in Kp. So no change in Kp. No change. Why are these subjective questions over here? Shouldn't it be all objective? For a gaseous reaction, the equilibrium constant Kp is something than Kc at 298. Oh, so like greater than less than something. So you can see that delta N gaseous is negative. That means it's PV. Sorry, it's RT to the power of some negative thing, right? And 298 Kelvin, that's close to 300. So it's it's bigger than one. Our RT value is bigger than one. So this is going to be less than that. A vessel at equilibrium contains N2O4 at a pressure of something and NO2 at a pressure of 2 naught. Okay. Now volume is doubled at new equilibrium. The pressure due to NO2 is this thing P naught. The value of M is and N is fine. So initially it just contains N2O4 and NO2 at pressures 4P naught and pressure 2P naught. Oh wait, what that means is like 2P naught squared upon 4P naught. This thing is our Kp value. Cool. Okay, and then the volume is doubled, right? At new equilibrium, the pressure due to NO2 is okay. Fine. So what we can do is just consider N2O4 only. So at equilibrium, what you have is that NO2 is 2P naught and this thing is 4P naught. So at the initial starting point for this initial volume, right? So for the first volume, this would have been 5P naught, right? So 1P naught just dissociated into 2P naught like that. And now if you double this, right? If you double the pressure because volume, no wait, volume is doubled. So pressure should be half. So this will be 5 by 2P naught if you do that. And then from it, some pressure leaks out. So minus X, and now we got 2X over here. So 2X squared upon 5 by 2P naught minus X is Kp. Right, and Kp is the same thing as just 2P naught squared upon 4P naught. So that works out. Right, so we can cancel this 2 out. You will just have X squared equal to 5 by 2 P naught. So 5 by 2 P naught times, and this should just be, oh wait, here's this 4 over here. So okay, 5 by 2 P naught minus X times this P naught, and that 4 goes over there. And that means 8x squared equal to 5p naught minus 2x times p naught, which is 5p naught squared minus 2x p naught. Right, so now this is a quadratic equation. You can solve this hopefully. So 5 times 8, that's 40. 40 and 40 can be written as 4 and 10. That's not going to work. 40 can be written as 20 and okay, that won't work. Something that has difference of 8. Come on, think of it. 40 is what? Like, this doesn't make sense. 40 can be written as, okay, we can't be just fooling around that, can we? So that's 8p naught. Yes, that's 8x square minus, so that goes on the front. Yeah, so difference of 2 for 40. Oh wait, so you have this radicals and stuff over there. That means you can kind of get the formula for that. Okay, cool. So what do you want to find? You just want to find what that thing is. Okay, so cancel this away, and this will be x is I should say x upon p naught is minus b is minus 2 plus minus square root of b squared. It's like 4 minus 4ac, so minus 4 into actually plus of 4 into 5 into 8 upon 2, so it's like 16. Yes. That's gonna be negative 1 plus minus square root of 1 plus 5 into 8, which is 41 upon 4, I think. Right, so mn, that is probably that means m times 10 plus n, because it's like in digits, right? These are 1-digit natural numbers, so hopefully this is what they are doing. And of course, you just take the plus value because negative value doesn't make sense, right? There should be some NO2. So the value of M is, I think M is 4 and N is 1. Right, so 4 and 1. Okay, cool. I'm going to write it like that. M is 4, N is 1. Question number 4. Oh wait, that's the question number 4. Question number 1 of the next section is, there's only one question. Huh? If equilibrium constant for the reaction is K, then for the backward reaction, the what is 1 upon K. So it's true or false for the backward reaction. But you have this, so no, it's 1 upon square root K. So it's false. Question number 2. Sorry, question 1 once again. Right, one option correct. Kp for this thing at at equilibrium pressure of 3 P naught is 0.5 P naught. On having the volume of the container, the equilibrium is distributed. The new equilibrium pressure is. So yeah, it's the same kind of question as previous one. Okay, so the same thing. Just have N2O4, N2NO2. What's it? So Kp for this thing is 0.5 P naught, and this is an equilibrium pressure of 3 P naught. So total thing is just 3 P naught. So just guess some solution directly. So 0.5 P naught, huh? Oh, I know. This is 2 P naught and this is P naught. Yes, because look at that, P naught squared upon 2 P naught. That's exactly what 0.5 P naught. Right, so this was easy. Okay, and on having the volume of the container, the equilibrium is distributed. Okay, so we know that this would go back to 2.5 P naught, I think. Right, and then you have the volume, so the pressure will increase. So now this will be 5 P naught, and then this minus X, and this is like 2X over here. So the new equilibrium pressure is, so like 0.5 P naught is 2X squared upon 5 P naught minus X. Right, so 5 P naught squared minus P naught times X, that thing is 8X squared. So hey, it's the same as the previous one. No, it's slightly different. So P naught X. So once again, you just have to apply the quadratic formula. Right. Hey, wait a second. Here, what did you want? The value of M is equilibrium, the pressure due to NO2. But wait a second. But then we just found what X is. We didn't find what 2X is. We should have found out 2X. Oh no. But yeah, the radical, it did contain 41, and that means it was probably correct, just that there was, I think, some minor calculation errors. It will work, probably. Right, so this should have 4 in the denominator and stuff. Right? Okay, whatever. So where were we? Question number 1. Right, the equilibrium pressure is. So let's solve this. X upon P naught is minus P, like minus 1. So plus minus square root of P squared. 1 plus 4 into 5 into 8 upon 2a, so 16. That's going to be square root of, okay, so you want 2x, right? So it's going to be upon 8. And just want the plus value because negative value don't make sense. So 8 times 5, that's 40, times 4 is like 160. So 161 square root of that minus 1. Wait, what? What? Something went wrong? No, wait, this doesn't make sense. That should be 8x squared. Yes, that is correct. But that's not what we got. Why is there this 79 and 70 thing over here? It should be minus b, and that is minus p naught. Why would it be anything else? Okay, let's just form the equation once again. We'll see what we get. So 2x squared, that's like 4x squared upon this guy's pressure, which is 5 p naught minus x, and that is equal to your kp, which is 1 by 2 p naught. So 8x squared is 5 p naught squared minus x p naught. It's the same thing. So minus p. Oh yeah. So wait, minus p would this? Yeah, it would this thing. The new equilibrium pressure, not just the pressure for NO2. So what we were doing was correct. It's the same thing. It's just 8x squared plus p naught x minus 5 p naught squared equal to 0. So we were doing it correctly, just that not x, we want more than that. So what's it? X is minus, okay, actually, x upon p naught, that's minus 1 plus minus square root of p squared, like 1 minus, okay, so this is going to be 60, so 161 upon 16. Right, that's x. We don't want that. We want the total pressure, which is this plus that. It's going to be 5 p naught plus x. So this plus 5, that's what actually you want. So 160 times 5 is 80. And then 80 minus 1, that's 79. It should just be plus over here. So 79 plus square root of 161 upon 16. P naught. Yeah. So it's B. Question number 1 is B. Question number 2. Same kind of question once again, Okay, 4 moles of equimolar mixture of Cl2N2 is added, 20 liter vessels. Okay, so Cl2 into 4 moles of an equimolar mixture. That means 2 moles of this, 2 moles of that. 20 liter vessel. Oh, this thing upon 20, this thing upon 20. Cool. 1 mole PCl5. Right, in our first 20 liter vessel. And 2 moles PCl3. Right, and 3 moles Cl2. Oh wait, okay, it's added to that, and all of this is just 0. Right, so after equilibrium is established, you will have 3 moles of Cl2 at equilibrium. Right. Oh, okay, the mole fraction of PCl5 at the new equilibrium is. So where's the PCl3 here? You just have Cl2 and N2. Okay, so this was already at equilibrium, and then you add Cl2 and N2 over there. Oh, okay. So initially also, like, okay, so this was just Cl2. Okay, so it's gonna be plus 3 mole Cl2. It was already there, and PCl5 it was 1 mole. Right, so it was plus 1 mole, and PCl3 2. Right, so this was the equilibrium condition already, and then you add this to that. So wait, what does that mean? That means we can find what Kc is. So Kc will be PCl2 times Cl2, which is 6 upon 20 squared, and then upon that, so it's going to be 6 upon 20. Okay, cool. And since the volume doesn't really change, all we care about is that the equivalent, like, mole equilibrium constant without considering volumes, that would be 6. Okay, cool. So yeah, Kc is 6 upon 20. So that's some information that we know. Now what do we want? You want to find the new equilibrium. Cool. So since you added Cl2 and N2 over there, it's gonna change. I mean, like, N2 just decreases the pressure. So yeah, but it doesn't change. Right, it doesn't change anything, right? It actually increases the total pressure, but the partial pressures remain the same. So we can kind of just ignore it, because if it's a constant vessel, constant volume vessel, you can ignore that. Right, and it's just that you added more Cl2. That's gonna go back in that case. So now just play 5 upon 20, then you have minus x. So 5 minus x upon 20, and then this will be 1 plus x. This will be minus x as well, because yeah. So what do you know? You just have 2 minus x into 5 minus x upon 1 plus x equal to 6. There we go. All that 20 stuff, it just cancels. Yeah. So solve this equation. Once you find x, you find everything. So x squared minus 7x plus 10 is 6 plus 6x. X squared minus 13x plus 4. What? That's 5 minus x, that's 2 minus x. Yeah, that is correct. for sure. And this should be equal to 6. Yes. Yeah, because initially it was just 6. Right. Uh, so this is in fact thing, but then the discriminant, yeah, discriminant is positive because 13 square is much bigger than 16. So yeah, we need to use the formula once again. So your x will be minus b is like 13 plus minus square root of b square, which is 169 minus 4 is minus 16 upon 2, which is, so plus minus, like, it's just going to be plus, because we know, if we know by Legard's principle, it's going to be happening. So 153 upon 2, 13 plus, okay, and what do you want? The mole fraction of PCl5. So it's going to be 1 plus x, okay, mole fraction, fine. So that's going to be, okay, just delete all of this. This was Cl2, this was PCl5, this was PCl3. Right, so mole fraction will be 1 plus x upon this added up, so 7 minus 2x. That's what you want to find. And x is this thing. Okay. Well, thank God there's no x square terms, but this is still complicated. Yeah. There we go. 1 plus x. It's going to be this plus that. It's like 15 plus square root of 153 upon 2 upon 7 minus 2x. So 7 minus 26. Okay, wait. You could just have that upon 2 gone. Okay, and then this will be 7 minus 13. Yeah, like, or you could have 14 minus 13. That's like 1 plus square root of 153. Actually, minus, because we did minus for the 153. Upon 2, this cancels. Yeah. Wait, we took 2x. Yeah, it's actually correct. It should be just minus 2 square root of 153, and then it would be very correct, right? Oh, come on, what am I doing? Just do it directly. 7 minus 13 is minus 6, so square root of 153 minus 6. But then that 2 comes down, and it's this thing. So it's none of these things actually. But shouldn't there be this 2? Yeah, it's gonna be 1 plus. Sorry, no, there's not that, because look, 5 minus x, 2 minus x plus 1 plus x, this should be just 7 minus x. Actually, not that in fact. Why is this even 7? It should just be 8 minus x. Yeah, that's better. So now this will be 16 minus 13, and that will be 5. Right, I think. It's going to be 5 minus square root of 153. And now the 2's cancel away perfectly. That's still not there. Come on. Seriously. Why isn't it there? Maybe we have to first of all rationalize this. But that's going to take a lot of time. So 225, and then it's got 25. And no way. It's not. I'm not doing that. The mole fraction of PCl5 at new equilibrium will be. It doesn't make sense, you know? You add more Cl2, so it should increase. Yeah, and previously it was just. Where are we going wrong? Where are we going wrong? It's definitely just 1 plus x upon 2 minus x plus 5 minus x plus 1 plus x, right? So that should be 8 minus x and like 1 plus x upon 8 minus x. The only way this could probably go wrong is if your x was. Oh, hey, that makes sense. Right, so x cannot be that big actually. It should probably be 13 minus. So yeah, it still works because 13 squared is 169. And that's why it should be like that. Right, x being that big would be a problem because it will just, maybe it will exhaust away the Cl2, who knows, right? Yeah, so x should be less than 5, I think. And maybe that quantity was not, yeah, it was of course not less than 5. So there we go, this is the actual thing. So instead of having plus over here, you should just have minus. So minus, and this should be plus. Right, so 15 minus that, and Okay, calm down. 5 plus, that doesn't make sense. I mean, it's gonna be 2 times, sorry, 16 minus 13, that's just 3, right? No, yeah, that's 3. So it's A, question number 2A. Question number 3. Okay, consider the dissociation of SO3, NH3, PCl5, and 2O4 in 4 different vessels. Which one of the following is correct? The average molar mass of equilibrium mixture of this thing, so dissociation of all of these in 4 different vessels. So average molar mass of the equilibrium mixture of this quantity is 50. Why? I don't understand this. 50 of all things. I mean, it's an equilibrium, so it's like less than something, that would make sense. But so dissociation of this in 4 different. How does NH3 dissociate though? Does it even dissociate? Can2 does, SO3 does. Oh, so it dissociates. Okay, so it's like NH3 plus N2 plus H2. Okay, so you know all of these dissociates, like their molar mass will be less than what their actual masses are. So for SO3, it's just 5 times 16, which is 80. Yeah, right. So it should be less than 80, which it is. Okay, for NH3, the mass is 14 plus 3, 16. Sorry, no, 14 plus 3 is 17. So it's bigger than 17, and that's not correct. For PCl5, so phosphorus, I don't know what the mass of phosphorus is. So yeah, just go to the next one, which is N2O4. Its molar mass. Hey, so yeah, it also changes because number of moles become extra. For N2O4, the mass would be 2 times of 14 plus 2 times 6, which is 32. So 2 times of 46, which is 92, I think. And this is in fact less than that. What's going on here? Oh, and it should also be more than NO2's mass. And NO2 is 46. Yeah, that's less than that. That's not making sense. Right? So it goes between NO2 and N2O4. And NO2 has mass 46 and this has mass 92. It should be between that. This is less than that. Doesn't make sense. Right, 50. What's the average molar mass of equimolar SO2 and O2 mixture? That will be average of those two. SO2, that's like 4 times of O2. Sorry, 4 times of oxygen. And O2 is once, I mean, this 2 times of, it's like 6 times of oxygen. Yeah, 6 times of 16. Upon 2, that's gonna be 3 times 16, like 48. And this is bigger than that, which makes sense. Yeah, it can definitely happen. For this guy, N2 plus H2, right? Okay, we already did this. It's bigger than what we thought it is. For this guy as well. Okay, we don't know what phosphorus has mass, so we're gonna skip this. A looks correct. Question number 4. 2 moles of PCl5 is heated in at some Kelvin in a 150 liter vessel in presence of 1 mole neon. At equilibrium, the mole fraction of Cl2 were found to be 1 upon 7. Okay, so PCl5 is heated. Fine. Mole fraction of Cl2 is 1 upon 7. If 4 moles of PCl5 were heated in 1 liter vessel in absence of, so heated at in a 150 liter vessel, and this is in 1 liter vessel. Okay, in absence of any other substance initially, then its degree of dissociation will be. Right, so we can find out what Kc is from this thing, right? So 2 moles of PCl5, right? So PCl5 initially had 2 moles, PCl3 and Cl2 had 0. Then this guy's mole fraction is 1, but then PCl5 also, sorry, PCl3 also has mole fraction 1 by 7. And that means this has mole fraction 5 upon 7. So it's in the ratio of 1:1:5. right? uh that means, so if I go backwards, then this would be like 6 became 511. So 2 would become 5 upon 3, 1 upon 3, and 1 upon 3, right? Yeah, because look at that, 5 plus 1 upon 3. Yeah, so it should be the thing. So it's just 5 upon 3, 1 upon 3, 1 upon 3. These are the moles. Cool. And what is that volume? It's just 150 liter. So that will work out, and that's like Cl2. And time is bigger, so it's going to be 1 upon 150. Right. Times all of this stuff. Actually, 3 times of that, because that's also 1 liter. Yeah, that's the actual moles, because and yeah, so it's gonna be 1 squared upon 5. That's this times 5. So 2250 something, right? 15 times 15 is 225. Yeah. So 2250, that is the total. That thing is just Kc basically. So now we know that Kc is just 1 upon 2250. All right, cool. And now what? In 1 liter vessel, and what? 4 moles of PCl5 are taken. Right. In 1 liter vessel, in absence of any other substance. Then it's, wait, it's like in presence of 1 mole of neon. Okay, so that being 1 upon 7, it is different. It's also taking neon into that action. Oh, come on. So all I did was wrong in that case. So this is PCl5, PCl3, PCl2. You didn't give us anything about equilibrium constant or anything. Okay. T Kelvin. So you didn't even give us about like what temperature is or anything. But it's just 1 mole neon, so that actually doesn't change. It's 1, right? And this was 2, so it's like this is now 2 minus x. This is x. This is x. So that's going to be x upon 3 plus x, right? That thing is the mole fraction of Cl2. It should be Cl2 again, and that will be what, 1 upon 7, right? I think 7x is 3 plus x, so x is 1 by 2. Cool. So x is 1 by 2. This will be 3 by 2. Both of these will be 1 by 2. This is Cl2. Okay, so this is now like that, right? And now we can figure out what Kc is. So it's gonna be 1 by 3 into 2 into, yeah, because that 2 will come down. Okay, cool. And then that times 150 liter, right? So this is our Kc value. So we finally got what Kc is. It's just 1 upon this, all of this thing. So it's 900. 1 upon 900. Yeah. Okay. And now what? In absence of anything, just take 4 moles of this guy in 1 liter vessel. So molarity is now 4. Sorry. Yeah, molarity is 4. And then 4 minus x, and then you got x and x over here. Okay, then it's degree of dissociation. Okay, so we don't degree of dissociation, then you should just have 1 minus alpha. This will be 4 alpha squared upon 1 minus alpha is 1 upon 900. So alpha squared upon 1 minus alpha, or I should say alpha squared is less than 1 upon 3600. That means alpha is less than 1 upon 600, which is negligible in respect with respect to 1. So you can cancel this out. And yeah, then this approximation works out, and alpha will become equal or approximately equal to 1 upon 600. And 1 upon 600 in percentage, that's just 1/6. 1/6 is 0.166, so on. So like, yeah, but that's not any of these, is it? That's differentiation. This is supposed to be that, right? It's supposed to be 150 times. Okay, yeah, that should be the thing. And it's in 1 liter vessel. Come on, now what's going wrong? Now it can't go wrong, can it? Oh, it should be 60, not 600. Then, yeah, then it's like 10 upon 6, which is 1.67 something. So it's A. Okay, question number 5. For this reaction, the equilibrium steam hydrogen mixture was found to be 40% H2 by volume. Okay, so mole fraction is just 4 by 10. Yes, because volume is proportional to moles. Right. The Kp is for this reaction. This thing is solid. Okay, this thing is liquid. Don't consider that. This is H2 going to H2O. And the okay, cool. And both are the same moles. That's very good. The equilibrium steam hydrogen mixture was found to be 40% H2. That means 60% H2O. So yeah, it's just 6 by 4. That's the 6 by 4 squared, right? So it's like 3 by 2 squared, which is 2.25. Yeah, that is the Kp. So question number 5, B. Pressure doesn't matter in this case. Question number 5 is B. Question number 6. Question number 6 is excess solid something on rapid heating in closed vessel develops a constant pressure of 4 P naught owing to the partial decomposition of solid into NH3 and HI. Rapid heating in a closed vessel develops a constant pressure of 4 P naught. Okay, so what's your equation? NH4I gives NH3 plus HI. Okay, this thing is solid. Okay, so this is gas, this is gas. But the pressure gradually increases further owing to the dissociation of HI. So then this thing dissociates to what? H2 plus I2. Right. The final pressure is 5 P naught Kp for this. Okay. Right. So it develops a constant pressure of this thing if we ignore this dissociation. Right. If this somehow doesn't happen. Owing to the partial composition of solid NH3. So NH4I into NH3 and yeah, okay, cool. And these both of these will have the same partial pressure. So both of them have 2 P naught. So you know that Kp1, that thing is 2 P naught squared, it's like 4 P naught squared. What about Kp2? Kp for this dissociation is okay, fine. But the pressure gradually increases further owing to the dissociation of Hi. So now it becomes 5 P naught. So initially it was 4 P naught, now it's 5 P naught. Okay. And right, so that means like more moles will be created. Of course, look, this thing, it doesn't change the number of moles. That's a good thing because that means this reaction cannot actually change the pressure. Only this reaction can change the pressure. And it changes the pressure by increasing the number of moles, and that's increased by 1 basically. So we just have this plus 0.5 P naught and 0.5 P naught in this case as well. So now this will be 2.5 P naught and 2.5 P naught NH3 and H2, but sorry, and HI, and this thing will dissociate into this thing, right? The final pressure at equilibrium is 5. Okay, Kp for this is all right. So this should also be there. Okay, so you can figure out what HI is from this equation. So this will be like this quantity upon 2.5 P naught. So this is 4 upon 2.5 P naught. That is what this actually is, and that means we can figure out how much of HI went away, right? So it's going to be 2.5 minus 4 upon 2.5 P naught. That's the pressure of HI that went away, right? So now we can figure out what that should be. Okay, so let's calculate. What is this value? And we know this is going to be like 4 upon 2.5 P naught now. Come on. P naught, and this is like H I and H2 and I2. We'll see what happens then. So this value, first of all, what is this value? 2.5 is like 10 upon 4, I think. This will be 16 upon 10, which is 1.6. So this should actually be just 2.5 minus 1.6. That means this is 1.6 and no, it's not 1.6. It's half of that because 2 of this gives 1. So it's going to be 0.8 over here and 0.8 over here. And then you have 2.5 minus. So no, that is, sorry, this value is 0.8. Sorry, this value is 1.6. So, you know, HI just went to 1.6 now. So 2.5 minus 1.6. What is that value? That is 0.9. That upon 2, that's 0.45. We finally have all the pressures now. So this will be 0.45 squared upon, yeah, upon 1.6 squared, which you can write as 45, like 160 over there. That will be 9 upon 32 squared. Okay, that's 81 upon, so this is 2 power 5, so 2 power 10, that's 1024. 81 upon 1024, so it's B. Question number 6B. Question number 7. Ammonium carbonate decomposes as this reaction. Okay, for the reaction Kp is given. If we start with 1 mole of the compound, total pressure at equilibrium would be. Okay, start with 1 mole of the compound. Wait, what? Oh, so you don't know the pressure at equilibrium, huh? Right. Okay, I get it. So say, right, so say this thing is just going to turn out to be 1 minus x, then this will be 2x and h3, and this will be x, right? And the total pressures, these people have mole fractions as x upon 1 plus 2x, 2x upon 1 plus 2x, and x upon 1 plus 2x. So this times the total pressure, that's the partial pressures, right? Now we can find it. So it'll be x times, well, just 1. So this is that, and this is like 2x squared upon 1 minus x. Wait, it's solid. We don't have to worry about this. Okay, this is solid. Fine. We don't have to worry about it at all. Because, yeah, this thing is solid. So NH3 is just 2 P naught upon 3. That has the partial pressure 2 P naught upon 3. CO2 has pressure P naught upon 3. And that means 2 P naught upon 3 squared times P naught upon 3. That thing is the Kp value. Where, okay, P is, you should use P. So P is the total pressure. Right. So you can figure that out. It's going to be what? P naught, sorry, P cube. And this is 4 upon 9. No, 4 upon 27 because 3 squared. Yeah, that thing is Kp. So P cube is, or I should say P is like cube root of that. So it's going to be 3 times Kp upon 4, the cube root of this thing. Correct. And Kp upon 4. Kp is 2.9 in power negative 5. Okay, that upon 4, that will be what? So 3 cube root of, okay, 2.9. So 0.7 is 28. And for 10, it should be 25. Right. Into 10 power negative 5. So you can get this out. 72. No, 72 is not a good value. We want the cube root, right? What cube is close to this? I don't know. 7, huh? Come on, think about it. Cubes. So 729, of course. So 729 is close. Like that's 9 cube. Wait, what? Yeah, 81 times 9, of course. What was I doing once again? And what's this? 10 power? 10 power negative 5. Okay. That's gonna have 10 power negative 3 over there. That's not a good idea. But 2.9 upon 4, that is 0.725. 10 power negative 5 won't do. It's gonna give us very bad results. Okay, then you just have to guess basically. So this is like 7.25 into 10 power negative 6. So you can take that out. It's like 10 power negative 2. So 3 into 10 power negative 2 into cube root of 7.25. 7.25. I think it's like it's smaller than 2. That's all you need to know. So something smaller than 2, that times 6, that times 3, that is going to be something smaller than 6. So yeah, by face value it should be either this or that or that. But okay, these are just too small. This probably doesn't even go well with it, right? It's definitely just like 7.25 square root of cube root of that, right? Come on. 729 would have worked if it was something like that, but no, it's not. Okay, 725 something, 7250. That's where we are going to be looking at, right? This works out like that. So 7250, where would we get that? We don't know. It's definitely, I think 0.0582. That's our best bet. Yeah, but then it's 10 power negative 2, so shouldn't it be different? It's 10 power negative 5, so okay. Come on, why? Why is this so complicated? Okay, this is not how it was supposed to go. What did I do wrong? Did I do something wrong? I don't know. It doesn't feel like I did anything wrong. Total pressure at equilibrium. Yeah, so 1 mole of the. Wait, what if that 1 mole just completely obliterates itself? Oh, that could happen, you know? Like that 1 mole just turning into this and that. So 2 moles of NH3, 1 mole of CO2. You didn't give us any kind of temperature, right? Oh, that is bad. 1 mole of the compound. What if it does that? What if it just becomes NH3 and CO2? And what temperature is it? What is the pressure that we're doing it? We don't know anything. We don't know anything over here. But total pressure at equilibrium, I assume it didn't actually completely obliterate. So yeah, that should be P naught upon 3 and P naught upon 3. And it should be like this, right? So it should be 4 P naught cube upon 27, that's equal to Kp. So yeah, like cube root of 3 times cube root of Kp upon 4. Kp upon 4 is just 0. So it is 0.725 into 10 power negative 5, and that's like simple 26. So that thing. So yeah, like none of these actually make sense. Actually, they do make sense because like 0.07, that's still 10 power negative 2 something, but shouldn't it be like by face value it should be 6. So maybe it's B. I think it's B. But then 7.2, and we're talking about cube roots. It could be C as well. Like this is close to 4, right? So 0.04, that upon 3, that's like 4 upon 3 is 1.33 something. So 1.3, that thing cubed, that could be, okay, 13 cubed is 169 times 13, which is 4027, is like 507. 0169, and that's like 791. Okay, so 2197, that's not the face value. This is not close to that. Right, so it's definitely this thing, 0.0582. So 7p. Okay, question number 8. And yeah, I'm running low on time. Oh, come on. Question number 8. Okay, NH4HS dissociates in a vessel at temperature Tk in presence of 0.5 atmosphere NH3. At equilibrium, the pressure due to H2S is 1.5 atmosphere in the vessel V2 initially evacuated. It what? NH. So, okay, it dissociates vessel some temperature 0.5 atmosphere NH3 is already there. Okay. At equilibrium, the pressure due to H2S is 1.5. Well, that's even nice because we know it just associates as NH3 plus H2S. So if that pressure is, and it's a constant, it's like the constant volume case. So yeah, that's really nice. That means the same pressure must have been because of the NH3 added. So now the total pressure is like 2.5 for NH3. So you know, like 2.5 times 1.5, that thing will now be Kp in that case. Cool. Right. In the vessel V2 initially evacuated solid dissociates at some Kelvin. So now there's nothing over the total pressure in vessel V is P naught. So it's like P naught squared upon 4 because P naught upon 2, P naught upon 2. Right. That thing is now going to be Kp. And the weight ratio of something is gamma, the value of P naught and gamma. So first of all, we'll find what P naught is. And this is equal to Kp. So it's like 1.5 times 2.5. So P naught square is just like 3 into 5 is 15. So yeah, square root 15. Wait, what? Yeah, that is square root 15. Oh, come on. No, wait, it's 1.5 atmosphere over there, so it should be actually 2 atmosphere, not 2.5. Why did I write 2.5? It's supposed to be 2. Yeah, there should be 2. So that's already just 3. So it's gonna be what, 12? So P naught is 2 square root 3. Cool. That means this option is strong. So 2 square root 3, 2 square root 3. And what you want the total pressure is, okay, in the weight ratio of NH3 and H2S. So both are the same number of moles. NH3 is 17 by mass and H2S is 32 plus 2 is 34. So it's 1:2, right? Huh? NH3 is 17 and H2S is, yeah, okay. In vessel V1, okay, that's different because this is now it's in like 2 is to 1.5, right? So 2 times of 14 is to 1.5. This time, that times should be like not 14, it should be 17 and 34. This is like this 2 is to 3. So yeah, the weight ratio of this is to that. That's 2 upon 3. So it's A. Question number 9. Okay, solid ammonium carbamate is heated in a vessel. At equilibrium, the pressure was found to be P naught. The volume now is half. At equal to P naught, the pressure, okay, equilibrium is re-established. Heated in a vessel, initially evacuated. At equilibrium, pressure was found to be P naught. So it dissociates, and then pressure is found to be P naught. How does it dissociate though? Solid ammonium carbonate. We don't know how it happens. NH2 over there. Okay, and you got this. Oh, so it's just like NH2CO minus plus NH4 plus. Okay, and then it should dissociate as this thing, NH2. Right, this plus NH3. That's how it should probably dissociate. And it's in a vessel. The equilibrium pressure was found to be P naught. So this was P naught upon 2. This was P naught upon 2. Volume now is halved. So you know that Kp is just P naught squared upon 4. Volume now is half. Yeah, at T equal to T naught, pressure is re-established. Well, this still just P naught upon 1, P naught upon 2. Yeah, just the moles are different. So at T equal to T naught, this is 2 P naught. Well, no, some of that will go back, right? Because yeah, It's solid. So A is just wrong. Kp for this thing is what? Right, volume now is half. At equal to E naught equilibrium is re-established. It should once again just be P naught upon 1, P naught upon 2. Very correct. Kp for this, okay. But it gives 2NH3 plus CO2. Well, that's different, okay. That's not what I thought it is. But still, it's the same thing. Like, pressures will be the same. So, instead of this, now we'll just have CO2. It's 2NH3, right? So, this will have so this will be P naught upon 3 and this will be 2 P naught upon 3. So this thing squared, okay, so just 4 P naught cubed upon 27 as we saw before. That is our Kp. So D is correct. Okay, and what T equal to P naught? This pressure plus that pressure is greater than 2 P naught. So the pressure of NH3 plus pressure of CO2, that's just P naught itself, because yeah, like no, it is the same as P naught. Kp is, yeah, so alright, the pressure will still be the same. And T equal to not P NH3 is less than 4 P naught upon 3. P NH3, it's 2 P naught upon 3. So yes, that's correct. And Kc for this reaction is 4 by 27. Kc is different, right? So P naught upon RT, that is N upon V. N upon V cubed. Yes, that goes very correctly. So this thing is actually correct. Yeah, nice. So C is correct, and D is at equal to P naught, P naught, CO2 is less than 2 P naught upon 3. CO2, yes. And the ratio this varies with time. No, it doesn't. So C is correct. Question 9 is C. Question number 10. 3x moles of PCl5 and 4y moles of CO2 are of CO are introduced in a rigid vessel of capacity V. On heating, two equilibriums are simultaneously established. PCl5 gives okay, and this other equilibrium. Which of the following is correct if at equilibrium? Cl2 concentration is x minus y upon V. PCl3 plus COCl2 constant. Okay, what? So simultaneously established. Fine. If at equilibrium, this is happening. Okay, cool. And 3x moles of PCl. Just if you do this. PCl5, PCl3, Cl2, and what was the other thing? Okay, CO, Cl2, and COCl2. Okay, 3x moles were there, and 4y moles of CO. Right. Okay. Capacity V. Right. On heating, two equilibriums are simultaneously established. Fine. Which one of the following is correct? If at equilibrium, okay, Cl2 has x minus y upon V, so its moles is just x minus y. Rigid vessel, right? So yeah, this thing is x minus y, huh? This thing is x minus y. Cool. Okay, and PCl3 plus Cl. Oh, so this plus that is x plus y upon V. Okay, so this plus that is x plus y, and this thing is x minus y. So you know what I'm thinking? Like this could be x and this could be y, right? Like this just gave y and this would be 3y and this would be 2x. That would be the thing, right? So this plus that, whatever this thing is, say capital X plus capital Y, that is x plus y, and capital X minus capital Y, that thing is x minus y. So of course it works out, right? So capital X is just a small x and capital Y is small y. Cool. We got the thing. Okay, now what? So you know what happens at equilibrium? So this thing will turn out to be 2x and this will be what, 3y? Right. So now the following is correct if at equilibrium this is happening. So Kc for the first reaction. So PCl5 giving this thing, right? So Kc for this reaction, that's just x into x minus y upon 2x and that times 1 upon v, of course. So A is kind of problematic. I would think. Oh wait, this cancels. So yeah, like no, not 4V. That's different, right? That is different. So no. KC for second reaction, that is okay. So that's there. V is always there. So x minus y upon 3 times what is this? Oh, okay. So 1 upon that. Fine. So V upon so backward reaction. Backward reaction would just have 3 times x minus y upon v. So this would be v upon 3 times x minus y. And that's still not this thing. So no, that's not what I want. PCl5 plus CO at equilibrium. This guy plus this guy. That's 2x plus 3y upon v. Yes, that's correct. So C is correct, and KC1 upon KC2 is 1.5 upon 1.5 is x minus y squared. And the first guy has KC x minus y upon 2v, and the other guy has, hey, where's that v and stuff? No, there must be some volume quantity over there. This is wrong. D is just wrong. So yeah, C is the way to go. Question number 11. Question number 11 is solubility of substance which dissolves with decrease in volume and absorption of heat will be aided by. So it dissolves with decrease in volume and absorption of heat. Well, absorption of heat, that means it's endothermic basically. So it will be aided by high temperatures. So yeah, and dissolves with decrease in volume, solubility. Okay. Decrease in volume of, like, I think the whole system, something like that. So we got that thing, like if it is decreasing your volumes, like if it was, for example, ice to water. So ice to water, you have a decrease in volume because ice is more volume. So, and when you increase pressure, it melts more easily. So if there's a decrease in volume, then increase pressure, it will work. If there's an increase in volume, then decrease pressure, that will work. Right. So here we have a decrease in volume, and that means you want high pressure for the forward reaction to happen. Right. So high pressure and high temperature. Question number 11C. The active masses of A, B, C are at equilibrium for this thing. Okay, and these masses are 0.5, 2, 1. Okay. Initially, the active mass of C was 0.5 and that of D was 0. That which is wrong. So, what's this thing? A, B, C, D. Equilibrium, it's 0.5. B is ABC. So for only ABC, it's 0.5, 2. So B is 1 and C is 1. D we don't know. Initially the active masses of C were like 0.5 and that of D was 0. Oh, what? Okay, fine, it's not that bad because like this is 0.5, that means the reaction must have gone forward, right? So you have now, right, so from there to there you can get a backward reaction. So that's 0.5, that means 0.5 will be added to B, so it's 2.5, and 1 will be added to A, right? Yeah, 1 will be added to A, and that will give us 1.5. This was the initial concentration, and then it happened, right? So C and D were increased. So 0.5 increase in C, 1.5 increase in D. That means this must have been 1.5 then. Yes. Okay. Which of these is wrong? The active mass of D at equilibrium is 1.5. Yeah, that's very correct. Okay. The equilibrium constant is this. God, calculation. Fine. So D cubed, 1.5 cubed. C 1B into a squared, so 0.5 squared. So you can write this as 0.5, sorry, get 1.5 into 1.5 squared, and this would then be just 3 squared, that's 9. So yeah, 9 into 1.5 upon 2, which is so like 9 and 45. 9 and 45, that's 3.5 upon 2, which is 6, like 6.75. 6.75 is the equilibrium constant. It's molar squared. Look, there's a cube over there, so this cancels. Okay, it should just be molar because the delta n is, yeah, it's just 1, so it's not molar squared. Okay, that is wrong. So 3 plus 1, 4, that's just 3. It doesn't make sense. The value of this quantity at equilibrium is 3.375. What? Kc upon concentration of D. So Kc is just 6.75 molar upon concentration of D plus concentration of A at equilibrium. That is this plus that, that's just 1.5. Right. So this quantity is 3.375. That's what we're saying. But you could have got rid of that thing. So like this thing upon 1.5 basically. That's just 9 upon 2. So 9 upon 2 is not that. Huh. No, wait, equilibrium is this condition. Then it's actually 2. So this is a 2 over there. Yeah, then it's just 6.75 upon 2, which is 3 point, let's see, 3. So 6 for 15 is 0.75, let's say. So 3.375. Yeah, that's correct. So D is correct. A is correct. Active mass of A is initially 1.5. Yeah, that's also correct. So A, B, D is correct. C is wrong. So question number 12, C. Question number 13. 4 moles of something dissociates in the 20-liter vessel at equilibrium. The active mass of Cl2 was found to be 0.1. Wait, just write this down. So COCl2 dissociates. So CO and Cl2. Okay, cool. 4 moles initially. 20-liter vessel. So 4 upon 20. Okay. At equilibrium, the active mass of Cl2 was found to be 0.1. Right. So 0.1 molar. Or you can say 1 upon 20, that would be like, which, sorry, 1 upon 10, which is 2 upon 20. That's at equilibrium. And of course, it just gives 1 of that, and that's also 2 upon 20. And this would be 3 upon 20. No, it's just 2 upon 20 as well, right? Right, cool. Volume doubled along with X moles of CO added. At new equilibrium, the active mass of, so first of all, from this expression you can figure out what Kc is. So Kc will just be 0.1 times that thing squared upon 0.1, right, which is 0.1. So now we know that Kc is 0.1 molar, sorry, right? And then what, the same thing, the same conditions, but you add CO, right? So X moles of CO added. Now this is going to be X upon, and what about volume? Volume doubled, so now it's 40, right? At new equilibrium, the active mass of COCl2 was found to be 1 upon 16 molar. Oh, so 1 upon 16, that's like 5 upon 40 molar. So 5 moles per 40 liters, something like that, right? Wait, no, that would be 5 upon 80. That's not what I want. To go for 40, that would be 2.5 upon 40. So it's like 2.5 upon 40. That is the equilibrium COCl2 concentration. That means like 1.5 moles. That's the change. Yeah. So X plus 1.5 upon 40. This thing is 1.5 upon 40. Right. So just find what X is. That isn't that like easy. So X plus 1.5 times 1.5 upon, actually, you know what, just scrap that. I'm gonna multiply by 2 anyway. So this will be 2x plus 3 upon 80, and this will be 3 upon 80, and this will be 5 upon 80 and stuff. So 2x plus 3 times 3 upon 5, and then you got 1 upon 80, right? That thing is equal to not 180, 1 upon 80, that is Kc, which is 0.1. And that means, uh, what's this thing? It's like 6x plus 9 is, so 8 times 5, that's 16 with it. So 6x is that the thing really? Looks like that. I mean, sorry, 8 times, it should be like 6 plus 9 equal to 8 times 5, which is 40. So 6x is 31. It's still not good because it's not divisible and stuff, but whatever. The value of x is slightly less than, more than 5, because 31 upon 60. So yeah, 31 upon 6. So it's slightly more than 5. It's B. 13 is B. Right, cool. We got it. Question number 14. A vessel was found to contain equal masses of CO and CO2, H2O, H2 at equal to T naught, at equal to 3 T naught. Mole ratio of this was found to be 9 upon 22, which one of the following is correct? So if this is an equilibrium question, then that means T equal to 3 T naught and T equal to T naught both would have the same concentrations and stuff, I think, right? So that reaction quotient wouldn't change. That should be happening. Okay. So what? Equal masses of this thing. Okay. And mole ratio of CO2 and H2O was found to be 9 upon 22. What's the mole ratio? Mole ratio initially though, if these are like equal masses, then it's just CO2 is, I think it's 44. It was like 12 plus 32. Yeah, that's 44. So like 1 upon 44 is to 1 upon what? CO2 and H2O. H2O is 18. So yeah, that would be like 18 upon 44. Look, the same thing. It's still 9 upon 8. So it's in equilibrium. So from T equal to T naught itself, it was at equilibrium. So Kc for CO plus H2O gives CO2 gives H2O. Okay, it's this thing. Fine. So CO2 is 1 upon 44. Right? Its number of moles is like proportional to that. So its molarity is proportional to that. For H2 to be 1 upon 2, because the masses are the same, right? Yeah. 1 upon 18. And for CO it's just 12 plus 16, which is 1 upon 28. Yeah. All right. And what's this calculation gonna give us? 18 times 28 upon 8. Yeah, upon 44 times 2, which we already did is like 9 upon 22. And this thing is 14. So 9 into 7 upon 11, which is 63 upon 11. So it's not 13. Come on, that's not the thing. It's 63 upon 11. So A is wrong. Mole ratio of H2 and CO at T equal to naught is 14:1. So this guy is H2. Okay, no. So 1 upon 2, that's for H2, and 1 upon 28, that's for CO. So yeah, it's just 14:1. So B is correct. There we go. Okay, let's go for C as well. So mole fraction of H2 at equal to T naught is mole fraction. Come on, 1 upon 4, huh? I'm not gonna do that. Okay, Kc for this thing is 1. Well, definitely not. So I'm just gonna assume B is the only correct option. Okay, and it is, in fact. This was only correct option 6. Let's go to question number 15 now. Hey, wait, what? Oh, it's changed. Fine. So 1 or more than 1. Right. Question number 1. For the gas phase reaction carried out in a vessel, the equilibrium concentration of C2H4 can be increased by. So this is C2H4 plus H2 gives C2H6. Delta H is negative. Right, delta H negative, that means decreased temperature that will work out. So decreasing the, okay, A is wrong. Decreasing the pressure, that will go to the more pressure side. So if this is gas phase, then it's left. And that's not good, because no, we want the equilibrium concentration of C2H4 to be increased. Oh, then that's good. So decreasing the temp. Okay, decreasing the pressure will in fact do that. In fact, increasing the temperature will also do that because the reverse reaction is endothermic. So cool. Removing some H2, yeah, that will do it. Adding some, yeah, of course. So all of them are correct. A, B, C, D. Okay, when solid NaNO3 is heated in a closed vessel, oxygen is liberated and NaNO2 is left behind at equilibrium. Addition of NaNO2 favors reverse reaction? No, no. These are solid states. They don't have that activity changing. So increasing temperature favors forward reaction. Uh, when it's heated in a vessel, oxygen is liberated. So it's endothermic. That means, yeah, like increasing temperature will favor forward reaction. Increasing pressure favors reverse reaction. Yes, it does. So C and D are correct. Question number, right, reverse it, of course. So question number 3. This equilibrium is attained at 25 degrees Celsius in a closed container and an inert gas, helium, is introduced. So closed container, the helium doesn't do anything. Which of the following statement is correct? So it do not change, of course, because it's closed container. Concentration of SO2 is reduced. No. Okay, more chlorine is formed. No, no. So A. Question number 4. Okay, for this reaction, the forward reaction at constant temperature is favored by. So decreasing pressure, of course, and what else? Like decreasing pressure, is it there? Okay, that's not it. Increasing the volume of the container. Well, that is the same thing. It decreases the pressure. So D works. What else works? Why are there okay? Why are there 5 options? I don't know. A. Introducing an inert gas at constant volume. No, no. That won't do anything. That won't change the pressure at all. Introducing chlorine gas at constant volume. No. Anything at constant volume is wait. Chlorine gas. That will go like that will do the backward reaction. So you want the forward reaction, right? Favored by. So it's not favored by that. Introducing an inert gas at constant pressure, that means the actual system's pressure will decrease, right? And that's good. Increasing the volume of the container, well, that's also good. Increasing PCl5 at constant volume, it's a gas, so yeah, it will work. It will work. So C works, D works. In fact, E also works at constant pressure or whatever. So C, D, E. Of course. Question number 5. For the reaction, this reaction at a given temperature, the equilibrium amount of CO2 can be increased by. The equilibrium amount of CO2 can be increased by. Right, so backward reactions be favored. Pressure has no effect, volume has no effect, adding a suitable catalyst, no. Increasing the amount of CO, of course, that works. Adding an inert gas, no. So D is the way to go. So 5D. So 6. Which of the following is correct about the chemical equilibrium? Delta G at constant temperature pressure is 0. Yeah, of course. Equilibrium constant is independent of initial concentration. Yes. Catalyst has no effect on equilibrium state. Yes. All of these are correct. Right? Reaction stops at equilibrium. No, it doesn't stop. It just goes dynamically. You get it, right? So A, B, C are correct. Right? D is not correct because both forward reaction and backward reaction go at the same rate. It doesn't stop. But yeah, as a net effect, you can say it kind of stops, but whatever. For this reaction, if alpha is negligible with respect to 1, then degree of dissociation alpha of AB2 is proportional to. Wait. Sorry. So if alpha is negligible with respect to 1, okay, so what's the thing? Then it's proportional to. So it. Oh, okay, I get it. So the thing is like this guy's pressure doesn't actually change a lot. So if you just initially had some pressure of AB2, then it would be the same pressure after dissociation. It doesn't change that much. And yeah, and that means like this is just P times alpha and that times P times alpha, right? Upon basically P, right? And that's the total P as well. I mean, P is also the total P in this case. And this is Kp. And that means alpha square is proportional to 1 upon P, yours, yeah. And for volume, it will be like If you had some moles initially, then this would be n upon v, right? So P is proportional to n upon v. So this is proportional to volume directly. So yeah, alpha is proportional to square root of v, and it's inversely proportional to square root of v. So C and D, I think. Right? So if you had some moles initially, those moles don't change that much, and then it works out. Question number 8. Consider the reaction given below. In which cases will the reaction proceed towards right by increasing the pressure? Reaction proceed towards right by increasing the pressure. So yeah, like that must be a lower pressure thing. So 4 plus 1, 5, that becomes 4. That works. 1 plus 4, 5 becomes 3. That works. Right. Uh, this doesn't work. Okay, because 2 becomes 2.5. No. 2 becomes 2. No. So A and C. Question number 9. Consider the reaction. Okay. Under what conditions shift is undeterminable? Addition of O2 and decrease in volume. Well, okay, if you add O2, then this goes to the right, and decrease in volume. That means like an increase in pressure instantly, and increase in pressure favors forward reaction. So yeah, both favor forward reaction. So A is not the way to go. Addition of CO and removal of CO2. No. B is definitely understandable. So no. C, increase in temperature and decrease in volume. Increase in temperature, that will favor the backward reaction, and decrease in volume, that means increase in pressure, that favors the forward reaction. So C is what we should go for. And what's D? Addition of CO and increase in temperature at constant volume. Okay, increase in temperature goes for the backward reaction, and addition of CO goes for the forward reaction. So D. Okay, for the reaction, the forward reaction at constant temperature is favored by constant temperature. Okay, that's good. And forward reaction just need to decrease pressure, right? So introducing inert gas and constant volume, introducing inert gas doesn't work. Introducing chlorine gas, no. It's the same question as before, I think. Introducing an inert gas at constant pressure. So this guy's pressure, system's pressure will decrease. So yeah, it will favor the forward reaction. Cool. Increasing the volume of the container, same thing. So C and D. Wait, isn't this the same question that was initially asked? It was some question like this. Oh yeah, so fourth and no, but this has 5 options. So, okay, whatever. So yeah, that's the way to go. Comprehension type. How much is it? Ooh, it's very big, and then there's assertion, reason, and whatnot. So I'm gonna go for that in the next video. Right. So answer key. Where is it? Where is it? Right. Get it. So first, no change. Okay. Second, less. M equal to 4, N equal to 1. Question number 1, false. Yes. Question number 1, B. B. Question number 2 is, oh, okay, that's B. Question number 3 is, why is this, what? Question number 4 is A. Why did that happen? I don't know. 9 C. C. 11 C. 12 also C. Okay, 13 is B. 14 is B. Then A, B, C, D. Yeah, okay. C and D. Yeah. A. Okay, cool. C, D, E. Cool. And then C, D, and then A, C, and then C, D, and then C, D. Yes, that's cool. So only question number 2 and question number 3 are wrong. Let's see what went wrong over there. Question number 2, question number 3. Go up. Question number 2. 4 moles of it. Okay, yeah, that calculation thing. And for question number 3, what went wrong? It should be C, the average molar mass. Okay, this is correct, and B is, sorry, A is wrong. Wait, question number 3, A is wrong. Okay, but wait, SO3. Look, O2 has mass 30. Sorry, O2 plus SO2 upon 2. That's like 6 O2 upon, so 3 O2. So 3 times, yeah, that's 48. That's still bigger than that. It should be correct. Okay, and SO3 itself, it just has 5 O2 mass. Sorry, 5 O mass. So yeah. Uh, yeah. Zp molar, of course. So 5O, that has the mass of 80. So it definitely fits in there. So between 40 and 80, it's 50. So average molar mass of this can be 50. Of course it can be. Why can't it be? I don't understand this. Like, just have some equilibrium very close to SO2 and O2. What's the big deal about it? It can definitely work. But you gave C as the correct thing. Okay, so I don't know what phosphorus is. What's the mass of that? Okay, do that next time. Question number 2 is wrong. They gave B as the correct thing. So 7. I have no idea how that worked out. Let's do it once again. So 4 moles of an equimolar mixture of Cl2 and 2 are added to 20-liter vessel. Okay, Cl2, N2, PCl5, PCl3, 4 moles of this thing to a 20-liter vessel. N2 is, oh, so wait, it's 2 of that and 2 of that. Okay, containing 1 mole PCl5 already. Oh, this was at equilibrium, right? So 0, 0, and 1 mole of PCl5 at equilibrium, and 2 moles of PCl3 at equilibrium, and 3 moles of Cl2 at equilibrium. The mole fraction of PCl5 at new equilibrium will be. So we know that the volume didn't change or anything didn't happen, right? So this added up would just be, so it will just go for moles in that case instead of going like this. What do you want? You want the mole fraction of, why didn't I consider this thing? I should have also considered N2. No, at new equilibrium. So yeah, I should consider N2 as well. Maybe that's why it went wrong. Look, N2 is 2. So what did we get? So I don't remember it. Okay, we will have to do it itself. So 2, 1, 2, 5. That's what this is at this instant. Okay, and then it changes to so more Cl2 is added. That means, and constant volume, right? So and this N2 doesn't do anything. So that means it's like 5 minus x, 2, 1 plus x. Sorry, yeah, 1 plus x, and like 2 minus x. So what you have is 2 minus x into 1 plus x. 0.5 minus x. What? No, sorry, that's not the way to go. So 5 minus x into 2 minus x upon 1 plus x. That's the same thing as this. So 6, yeah, 3 times 2 upon 1. Cool. So x squared minus 7x plus 5, that thing is 6 plus 6x. So x squared minus 13x minus 1. Wait, what? Oh, this is supposed to be 10 over there. So it's like plus 4 equal to 0. So x is 13 plus minus square root. So it's going to be minus. We know that. So 169 minus 16, that is 153 upon 2. So that is x. Now we know that. Okay, so that's good and all. And what do you want to find? You want to find the mole fraction of what? Of PCl5. Look, that is 9, right? No, not 9 actually. So 5 plus 2 plus 1 plus 2, that is 10. Okay, and then minus x plus x minus x, that's just minus x. Right, so 1 plus that, and then 10 minus that. So 15 minus square root of 153 was okay, once again, what was the question? Like, okay, x minus 5 into x minus 1, sorry, x minus 2 upon 1 plus x is equal to 6. So yeah, there's only one x squared over here, so don't have to worry about that. This is actually correct. So it should be like 15 and stuff over there, right? And this is 15 minus, okay, that upon 2, of course, that upon 10 minus x. So 20 minus 3. Okay, yeah, that's 7. 7 plus 2. 53. There we go. It should have been like this. So yeah, that's correct. And because I didn't take N2 into consideration while finding mole fraction. Happens sometimes. So, but really, I just spent so much time trying to do this. I should have skipped this if it was an actual test. So yeah, I'll see you guys in the next video. Bye.